It's a great pleasure to have Amaury Triaud with us, co-discoverer of the TRAPPIST-1 system. If you just say that again, it's such a special thing to be involved in, and really excited about your talk today on the temperate planets, unlike those of the solar system. Please go ahead.
All right, well, thanks a lot. And thanks again after I reach out, to accept that I come here, give a talk, and have that discussion. I think it's very important that we indeed talk. So first, so today I'll do a few things. First, I'll present Birmingham, a little bit the group that we have, and then I'll go for proper into the topic. Also, I don't mind being interrupted. So if there's a word of jargon, I realize that, a department different from the usual crowd that I talk to. So if there's a word you don't understand or concept, raise your hand. I don't mind going over it. Hopefully I've got a slide to explain it. Otherwise, I use my hands. So Birmingham, I don't know if you've been to Birmingham, but Birmingham looks like that. Do come to our campus. It's a very beautiful campus. And this is the view from physics and astronomy, which is great. Usually physics is in one of either the ugliest or the second ugliest building in a campus. Usually the other ugliest one is architecture for whatever reason. But here we have a beautiful one. Our group is small but growing very fast. So Yvonne used to lead the group, and now she's almost retired. She had the Royal Astronomical Society's gold medal a couple of years back. Bill Chaplin then took over from Yvonne, but now he's head of school, so he passed on the baton to me. And then there is Guy Davis, who works on the sun and stars, analyst, who does all three, sun, stars, and exoplanets, the group's name. And we just recruited Angelique, who is working on exoplanetary atmospheres, and we are opening new positions as a university, and I hope to have one more person there. So we have 7 postdocs, 7 students, and we are involved in all sorts of experiments, and I will show you some of ours. And right now is also a time, to advertise. So Birmingham is pushing an ambitious agenda. We're opening 125 new positions across the university in assistant professorships and full professorship as well, and it goes at a rate of about 30 new positions every 3 to 4 months. And so the first call has ended. The second call will soon appear, but I thought I would advertise that because it's a great way to join first the School of Physics, but also any of the other schools, and including what you're doing here, for instance, would be something that I would welcome to see in Birmingham. The advantage of Birmingham, I think, compared to many other universities, I don't know exactly, probably it's also true for Durham, is that we really have all of the panel to study habitability and the search for life. We have biologists, we have geoscientists, we have atmospheric physicists, we are in astronomy, and so it's a great place to continue to look at that. So that's the end of the advertisement. Here's the beginning of the talk, so you get to see all of the sponsors again. And the first thing that I'll do is first describe the actors that take part in that research, and those are the telescopes. So the first that you see right behind is called Speculas. Speculas means, means the search for planets eclipsing ultra-cool stars. It's a bit of a stretch, but it's TRAPPIST that Peter mentioned was the prototype of Speculas. It was to show that we could do things, and actually the funding drive for Speculas started before TRAPPIST-1 was actually discovered. But the idea is the same. So we have 4 telescopes here in the Atacama Desert, where the Very Large Telescope is located. 4 telescopes are accompanied by one in Lower California in Mexico, and one in El Teide on the Canary Islands, and soon a second one maybe. All of them are monitoring ultra-cool dwarfs, the smallest stars of our galaxies, in order to search for transiting rocky planets. And I will give an outline of that. One interesting thing that those telescopes have is that they have direct drive telescope mounts. And why is that relevant? It's relevant because of this telescope. This is ASTEP Plus. So ASTEP means the Antarctic Search for Transiting Exoplanets. This is Concordia Station on the Antarctic plateau. It's at 1,200 kilometers from the sea, 3.2 kilometers in altitude, mostly ice. And from that unique vantage point, we are doing extraordinary research. So it's a small telescope, it's only 40 centimeter, right? It's a very modest telescope, but it's a pathfinder to do other things. And so I'll hope to convince you that Antarctica might actually be the best observing site in the world, and hopefully we can place more interesting facilities there, notably related to the search for exoplanets and the study of their atmospheres. So both ASTEP and Speculas work with photometry. So we measure the brightness of a star, we hope for the planet to pass in front of the star and create a transit. That's how they work. I also work with spectrographs. So this is SOPHIE on the 193 centimeter. This is the telescope at the Observatoire de Haute-Provence that found the first exoplanet in 1995. And here we have HARPS and Espresso in Chile on the 3.6 and the 8-meter class telescopes out there. And so those take high resolutions spectra. We use those to measure accurately the velocity of the star, and we use the Doppler wobble method in order to infer the mass. So we detect the planet through the mass, which I consider its most fundamental parameter. Okay, why study exoplanets? So I think that question many people can answer slightly differently. For me, what drives the field, what drives me is to find eventually evidence that life has emerged elsewhere. But as we discussed with Peter, to me, this is not enough. What I want to find is actually what frequency does life exist in the universe and under which condition it does. And that tends to change a bit the focus of where we look at. Also, I think astronomers are still part of a very old and not scientific storytelling tradition, which is trying to tell the tale of our origins. And so finding our Earth and the solar system compared to the rest of creation is very important. And so just describing the results, I think, for people to understand where we stand as a humanity, how Earth was created and all that seems important. And what really drives a lot of my research is to understand the physics of planet formation as well. And the next slide will illustrate that point of why there is interesting physics in planet formation to find. Then there's a bunch of other topics here, which I think are more pointed questions, but hopefully that also make us dream that eventually exoplanets allow us to observe new climates, maybe measure climatic tipping points, because we have the chance of observing more than one Earth, and all sorts of other things in there. So this is the plot that illustrates the point about physical laws in exoplanets. So like for instance, the search for life, has been written since Epicurus, so that's nearly 2.5 million years ago. And at the time, Epicurus was part of the school of thought that everything, was possible. But as a physicist, we know that not everything is strictly possible because physical laws, shape the universe. And yet, when you look at a plot like this, where you have mass, this is units of Jupiter. So Jupiter is there, Saturn, Uranus, Neptune, Earth here, Neptune, Venus here, Mercury and Mars are below the plot. When you look at a plot like this, it doesn't look like it's shaped by a particular law. Like it's a mess of several clouds of points. And I think that's why studying the physics of planet formation is interesting, because it suddenly, it defied our expectation, all of those dots. The other point about that plot is that as exoplanetologists, we usually use that plot to say, hey, this is great. See how much we've detected. We've detected things pretty much in every part of the diagram. The lower corner here, this wedge, is because it's hard to detect low mass object at long orbital periods. So it's not too surprising that this is very sparsely populated. And we also use this plot to say how diverse exoplanets are, how wonderfully diverse it is. But I'll show you that actually this plot only shows a tiny fraction of the diversity that we could have in the universe. Because there's a third axis here, really, that comes out, the axis of stellar type. So this histogram here shows the type of stars that exist in the solar neighborhood and by extension in the rest of our galaxy. You see here units of solar mass. So this is the sun, and solar type stars are located here, 1 plus or minus 10%. Only 15%, 15% of stars in our galaxy are solar type. And half of those are binary stars. So they are pairs of stars. And so they're mostly ignored. So really, this plot is about 7 to 8% of the stellar content of our galaxy. And that's where most of the observations have happened. 7 to 8% of the galaxy. Most of the other stars are here. They're low mass stars. And so a big chunk of my research is happening there. And I've decided to dedicate what I do with exoplanets to this number, which is a huge number, and a huge number of things that are not in the solar system. So half of stars that we see at night are binary stars, and most people discard binary stars and search for exoplanets, so I study them. We don't have a binary star in the solar system. Half of stars have masses less than a quarter of the sun, so this is by far the dominant result of stellar formation and likely of planet formation, so I study that. And then half of single sun-like stars have a super Earth, and I forgot to describe that. So this is this region here, where half of sun-like stars have something more massive than the Earth within Mercury's orbit in this box. So half of sun-like stars have something we don't have in a solar system, and so I will be studying these super Earths as well. So everything that we don't have, which looks like it's normal in the rest of the universe. I'll place a comment here, especially for you since you're interested in habitability, but I would say that the old strategy was to identify Earth twins orbiting solar twins, and really I'm not at all in that movement. It doesn't mean that so Annelies Mortier, who works in our group, she tries to look for Earth twins around solar twins. I still think it's a completely viable research path. It's just not the one I'm taking. I think an alternative path is also just as interesting. The way I view things as well is that I've been a little bit ambiguous about the use of the habitable zone. And that's because when I talk about habitable zone with the public, people always think that you can go and pitch your tent on an exoplanet in the habitable zone. And that's really not what it's about. And also, I find that there's a lot of theoretical work that goes on defining the inner and the outer edge of the habitable zone for this and this criteria. But the more we investigate the problem, the more we see there are caveats, and you can move in and out depending on your planet. And so suddenly it looks more and more empty in that I want really what I want the habitable zone to be is something that tells me where to focus my attention. It's a sort of prioritizing parameter. It's not something, I don't care if the planet is not exactly in a habitable zone. So the way we've defined our search with Speculas, and ultimately it ended up just by chance somewhat with the rest of my research, is to look for temperate exoplanets. And the definition is a flux between 4 times and a quarter of that of Earth. And the reason is we go for planets that would not be habitable, either because they're too hot or too cold, because that's also interesting to find out and to test the limits of habitability, of the presence of liquid water on other worlds. We somehow need to observe worlds that do not have that liquid water. Otherwise, it doesn't mean much. And so I have several ways of organizing my talks and my research, but today I decided that I would focus on temperate worlds. And so here is the menu, so to speak. So with Speculas, we're looking for temperate subneptunes and Earth orbiting low mass stars. I will also describe very briefly the search for temperate circumbinary Jupiters, and that's with the spectrographs HARPS and SOPHY, and a little bit with the Antarctic telescope. Then I will look at temperate Jupiters around sun-like stars, and that's mostly with the Antarctic telescopes. And then this I won't talk about now, but we just have like actually a paper in prep at the moment on the temperate gas giants orbiting an M dwarf that we also do with Speculas. So the idea is really to study the range of fluxes on these planets, provide a sample of planets where we can study the atmospheres of these planets across most spectral types that we can. So what does it look like in practice? So what we have here, so this is that temperate zone here. We have stellar mass and incident flux. So you see the sun is here, and these are M dwarfs, ultra-cool dwarfs, so typically below 0.15 solar mass. And you can see that there's a growing population here of planets entering this broader temperate zone here. which is becoming the focus of more and more observations with the James Webb Space Telescope. And with Speculas telescopes, we do two things. We spend 80% of our time looking for new planets orbiting our triple dwarfs, like, for instance, TRAPPIST-1. And I'll show you an example of such a system, actually, that we've discovered last year. And also about 20% of the time we use to follow up things that others find, notably TESS. And at that game, Speculas became quite good because we have now about 50% of planets in the temperate zone that have a radius less than twice that of the Earth have been somehow observed, confirmed, or discovered by our telescopes. And so we're really, I think doing a great job at identifying all of those objects and getting them ready for atmospheric characterization. Here you can see TRAPPIST-1 quite well. In terms of new discoveries, so TRAPPIST-1 is also called Speculas-1, and that's because it was the first planet in the Speculas target list. We've identified in the summer of 2022, the press release came out the day that Queen Elizabeth died. So obviously this was not as important and it was missed by most people. But here is two planets. So both of them are slightly larger than the Earth, and you can see one of them is quite low equilibrium temperature, very similar to the Earth. Both of them are temperate, just about for that one. And you can see the quality of our data. So this is the telescopes from Chile. It's unambiguous that the planet is there, right? It's really easy to find rocky worlds. In fact, our telescopes are really good for these low mass stars. That's because they intrinsically faint. And TESS, the current space telescope, is only a 10-centimeter telescope, whereas our telescopes are 1 meter. So we have 100 times more flux with them. So this here is an exercise of injection and recovery. So in that area, all of the planets, depending on the color bar that you have here, are recovered. So simulated planets are recovered if they're injected into the data. You can see that TESS had something like a 20% chance, I think, no, maybe a slightly more, of finding the inner one, and almost a 0% chance of finding the outer planet. Whereas with the same data, our telescopes do a lot better. And that's really the key, is that even though NASA launched TESS, so in most people, TESS was meant to detect rocky planets and to detect habitable zone planets. But actually, if you read the proposal, it could detect rocky planets and habitable zone planets, but not rocky and habitable. And that's because the telescopes are themselves a little too small, but our ground-based telescopes here beat NASA, at their own game. I like that, It's like little guys, yeah, so in the proposal, when we set out to construct the Speculas array network, we said that we would find across the next 15 to 20 years, 20 to 30 planets. And now we are at 7 in TRAPPIST-1, 2 in Speculas-2, and we just got a paper accepted in Nature Astronomy for Speculas-3. And actually, as I was coming in a train, we have another candidate that emerged in the data. So it's picking up. We are half of the way to a third of the way there. So going well. The idea is to find many rocky planets. As part of this, I had the pleasure of writing a paper lately. It came out in December in Nature Astronomy on a concern of mine. So I thought it was weird about the habitable zone that, we had all sorts of language to describe biosignature and a search for life, but we didn't have any empirical traces for habitability itself, for the presence of liquid water on a planet. And I thought, okay, we need to be able to test that. Ultimately, I'm an empiricist, and I want to test. I want to observe and find stuff. And so the idea we put forward is actually not a novel idea in geophysics. We know that very well, but the idea is that planets are born with a lot of carbon. Certainly Venus has been, the Earth as well, and so has Mars. And the reason we don't have much CO2 anymore in our atmosphere is because of water. So through the carbon silicate cycle, carbon is sucked out of the atmosphere and into water bodies, and then it's sequestered into the crust. And so it means that we can, by careful comparison, so say that you have a temperate planet here, but has no carbon cycle, you might expect that it has a lot of carbon dioxide in its atmosphere. But that if your planet has liquid water, then water has been actively removing that carbon dioxide from the atmosphere and hopefully burying it. And the idea is that from a lack of depletion of carbon dioxide, one might be able to create a new tracer for the presence of liquid water. In that paper, what we outline is that it's important that you have more than one planet in the system, and that's for calibration purposes, really. We don't know ultimately with what amount of carbon planets were born with, and so we think it's very important that there are other planets so that that comparison can be made. Now, these numbers are just indicative. Even a small amount of carbon depletion is important. For instance, if you had an atmosphere at 95% carbon dioxide here, and the next planet was at 70%, you still have to ask yourself, where has that carbon dioxide gone? And at the moment, we can't find of any ways of stripping an atmosphere of carbon dioxide except liquid water. The paper has a long list of false positives and false negatives. So false positives meaning a deficit in carbon caused by some other process than liquid water, whereas a false negative that there is no deficit in carbon, but the planet still has liquid water. So we don't find any false positives, and that's mainly because of us and the team of geologists we work with of exploring the literature, and it's mainly from industry sources, oddly enough, because of solving the climate change issue. Many people have been looking at novel ways to strip our atmosphere of CO2, and all of these solutions involve usually superheated water. So always water. So at the moment, water seems to be a really good source and a unique source for removing large amounts of carbon dioxide. In terms of false negatives, we could find many. We could find like 4 or 5. Whether they work, so it means that there could be planets that have liquid water where you wouldn't have that deficit in carbon, but that's okay. Maybe there are other ways for us to find out what's going on the surface. So on one hand, the paper proposes, this. We also propose to name these things like we have biosignature to call them hab signatures, because there was no word for empirical traces of habitability. I think the word is really ugly, but we couldn't find a better word. So if you can find a better word, please be my guest. And we also put forward a proposition for observations, like a pathway to finding out whether planets indeed have liquid water oceans through the use of that new signature. Now, you can see here, this is a transmission spectrum. I will explain a little more later how those are created, just in case those don't happen. But you can see CO2 here as a band is very visible, because even if your atmosphere has very little CO2, and we know it from climate change, it's actually creating a big feature and easily detectable. So we think that a program could go to first detect CO2, identify that the planet has an atmosphere, to then measuring more and more the atmosphere of that planet in order to measure the relative abundance of CO2 in various planets of the same system, and thus establish whether some of the planets are likely to have a liquid ocean. So the main premise that came out of that was an observation in the solar system that there's as much carbon dioxide in the atmosphere of Venus as there is trapped in Earth's ocean and in Earth's crust. So there's just the same amount. Actually, just in the ocean nowadays, there's about 2 bars of CO2 dissolved in the ocean. So if you were to remove all that from our oceans, then our atmosphere would suddenly be, 3 bars, which is crazy, right? And that's what I mean. And our oceans are not very deep compared to what we could imagine. So it's a very, very good sink, very effective sink. So if we were to find, 98, 70, 98% CO2, then we'd have to ask, why is that 70%? It turns out, so here is actually this carbon dioxide feature here, again, as a function on the vertical axis of the transit depth of the planet. And you can see here various fractionation of CO2 in the atmosphere, and you can see you can measure that fairly easily, at least down to about 1% content in an atmosphere. So it's very easy to detect. So 10 parts per million is roughly the precision of the James Webb Space Telescope, the ultimate precision. So it means that on a typical exoplanet, here it's TRAPPIST-1F, we could detect, if we had great data, that is, we could detect all the way down to 1% content in CO2. So very, very strong limits. The other advantage of observing is that here, we know that there are contamination, so atmospheric spectra can be contaminated by stellar inhomogeneities, so spots, faculae, and stuff. And most of the uncertainty related with that contamination is high in short wavelengths and gets lower with longer wavelengths. And here is the photon noise uncertainty. And right where both meet, we have our CO2 feature. So it's the best spot also to observe, to minimize the contamination noise and maximize the photon noise. So it's one of the best places where we can possibly observe. And it turns out that in the same window that we observe, so this is the CO2 feature, you also have the methane feature and the carbon monoxide feature right next to it. So if your planet, for whatever reason, instead of having an oxidized atmosphere, has a reduced atmosphere, then you would be able, again, to detect it in one observation, in the same observation. And then as we were working, so Julien, my co-writer, my main co-writer, Julien de Wit, noticed that we have also here an ozone feature right next to the CO2 feature. And that this is actually pretty easy to detect as well. And it turns out that, well, CO2 sequestration at the moment is 80% done by the ocean and 20% by biology, by biomass. And so if we were to detect a depleted CO2 feature and also the presence of ozone in that location, then we might have a reliable biosignature. And so that's the proposition we make. And now I'm waiting for the red bullets to come flying. But there we are. I will now change tack and go to circumbinary planets. So I don't know if you want to ask questions now, or should I carry on? Carry on? All right. Circumbinary planets. So that's a big hobby of mine. The setup there is that you have two stars. They orbit one another. And around the two stars, you have a planet going about. There's an area around the two stars, which is called the unstable or instability area. And any planet that goes in there is ejected in a couple of orbits. It's really, really effective. But if you're outside, you can have chaotic orbit, but stable over the long term, and that is fine. And so that limit is about 5 times the orbital period of the two stars. So if this is 10-day orbital period, and at 50-day, your planet can exist. And typically, we find the innermost planets at about 6 times the binary period, so 60-day period in that example. So these are long-lived orbits. They're hard planets to find. The first one were found serendipitously in the Kepler data. So here was the data. You have here the photometry, so the brightness of the stars. You see here the two stars eclipsing. So what's in blue here is in blue, yellow, yellow, etc. So you have star B passing in front of star A, the opposite. And you can see the binary orbit here from the repetition. And then you had one event here, one event there, and one event there. And the time between this and that was not the same as between this one and this one. So normally, when you have a single star, your planet transits at every orbit almost exactly on the spot. But because here a source of light keeps moving, sometimes you catch it there and sometimes you catch it there. And so this was a telltale sign that this was a planetary signal. There are no known false positives in astronomy that can create this signal. So it's difficult to find, but once you find it, you're sure. That's the advantage. Then, in addition to that, there are various, dynamical effects between the orbits of the planet and the stars that further confirm that and allow us to measure parameters such as the mass. So that's the scene. Why are we interested in circumbinary planets? So I'm interested in them mainly for the study of planet formation and the core accretion model. But I've been thinking about that they might have a unique role to play in the search for temperate worlds as well. So because those, during the formation process, so the reason why their binary stars are interesting for planet formation is that when you have two stars that orbit one another, what they do is launch waves in the disk of material from where planets are born. And those waves prevent planet formation, meaning that the planets need to form far from the binaries. And this has been confirmed over and over again by numerical simulations. There is a very simple equation also that shows that you shouldn't expect planets exactly there. So we expect them to form far, and then the planets need to migrate. We think this disk migration, so it's an exchange of angular momentum between the planets and the disk in which they're born, has also happened around single stars. But around single stars, so if you remember, just swing back to the plot. So we think those planets, might have formed, maybe here and moved a little or something like that, but pretty much close to where they formed. These objects, we know they cannot form locally, so they must have formed far and then moved in. These, the super Earth and the sub-Neptunes, we don't know. Some people think they formed far and migrating, and others think that they formed from here, in situ formation. And at the moment, as far as I'm concerned, both scenarios are just as likely. And so around single stars, it's just impossible to distinguish one population from the next. But around binary stars, we know that the in situ population cannot have existed. And so we can isolate one population, find out its properties and all that. But another aspect of that migration is the following. So imagine you have two planets that form far and migrate. You can select a binary such that the planet would stop its migration right next to the instability limit. And the reason you would do that is because the binary stars themselves create a gap corresponding to this white zone into the disk of material around the star. So as the planet travels through the disk, it suddenly sees a hole, it stops just before the hole is. Around a single star, that planet would have gone right next to the star. And so if we do that in terms of a population, remember 50% of sun-like stars, single sun-like stars, have these sub-Neptunes and super-Earths, where they would all congregate right into the temperate zone. And so by carefully selecting which binary we want to observe, we might actually have quite a lot of temperate planets that we can sort of pre-select that way. Another reason why circumbinary planets are interesting on an atmospheric point of view is to do with seasonal variation. So this is where we observe from. Every time our planet goes through this line, it goes in transit and we can study its atmosphere. Every orbit, it does it exactly at the same time for single stars. But when we have two stars, we have two effects that happen. First, the two stars orbit one another. So we have already a little bit of an orbital arc. So you can observe the planet when it's here and when it's there. So if it's January here, it ends up being end of February over there. But another thing that happens is that the planet receives also a varying flux. So you can see here these two stars orbiting one another. Here is the traditional habitable zone, and the planet is here in blue. And so that planet receives a varying flux on the time scale of the binary orbital period or half the period, depending on mass ratio of the two stars. And so we can receive, or we can have on a second binary planet the effect of a seasonal variation, and thus the study of how an atmosphere reacts to changing conditions. And I don't think that this is possible at all for planets orbiting single stars using the current methods that we have. So although it's a difficult thing to do and measure, if this is something that we want to measure in order to assess certain, for instance, biomarkers, then circumbinary planets will be the ones to do it. I'll pass that slide. It has to do mainly with how do you say, planet formation. All right, so now a quick recap on exoplanetary atmospheres to show, to go back to circumbinary planets, because they're interesting in some way. So transmission spectroscopy, I'm not sure everybody knows what it is. Everybody? Yeah? Yeah? All right. So transmission spectroscopy, okay, it happens when the planet passes in front of the star. We have transit depth here, so the size of our planet is a function of wavelength. When it goes up, planet is more opaque, and we have a spectrum. We also have emission spectroscopy when a planet is about to go behind the star, and here we measure the same thing as before, except that instead of size, here we have flux, and here we see the planet is opaque. It's hiding its own flux in a way. And an element of that are phase curves. And I like phase curves a lot. The reason I'm introducing that is to show you something a bit special. The advantage of phase curve is that here, so we see the day to night variation, and here we can measure the night side temperature of our planet, the day side temperature of our planet, where these peaks tells us about wind speed as well in the planet's atmosphere, where how the heat gets redistributed from midday, which would be during transit here, to the east. And another aspect that we can do with exoplanets is to create maps. So when the planet goes behind the star, we can create during the ingress and the egress a sort of map of the flux. And when we combine those, we can get a sort of topography. And that's where things get a little interesting, because if we can get maps, then we can maybe locate where a certain molecule has been produced on a certain exoplanet. So how do we know about that? The advantage is to use a high resolution spectroscopy. So here is a spectrum of carbon monoxide, and we can see that it has a lot of absorption bands. And those absorption bands create a pattern here, which depends very much on the molecule, the atomic weight of the molecule. So it means that this is unique for this molecule, and it's actually even unique for this isotope. So carbon 12O or carbon 13O will have a slightly different pattern. And so it means that we can uniquely identify molecules, and including isotopes. The way the observation happens is done in this seminal paper by Ernest Nellen. What you have here is the orbital phase of your orbit. And what we resolve is the motion of the planet. So whereas most of the other methods relied on observing how the flux from the star is transformed by the planet, we actually resolve directly from the planet. So what you see here is each of these lines here corresponds to a subset of some of these lines, so 3 or 4 of them. And we see that they're moving here by hundreds of kilometers per second because the planet itself moves by hundreds of kilometers per second. The star is almost static in this case. You can do transmission. So the planet's atmosphere would absorb sunlight, but here it's mainly in emission, and one could do it also in reflection in many ways. So why is that interesting, and how is that related to binary stars? So the program that I have about binary stars was actually a sort of a stealth program to study this high resolution stuff and do exoplanet atmospheres eventually. And the reason is because ultimately, at the moment, we don't know what our planet's atmospheres are, and we're trying to detect a tiny signal in all of the noise created by the star, but also our instruments. And I thought, well, what if we use the same method to find something that we know well? And it turns out that the stars that we were using had a sun-like star and then a weak secondary star, which look like stars like at the center of the TRAPPIST-1 system. And so we can get a spectrum from these stars very well when they're in isolation. And when they're in a binary star, the flux ratio between the sun-like star and a faint star is similar to the flux ratio that we have between a star and a planet. And it turns out because those stars are really small, they actually have almost the same size as a planet and almost the same temperature as a planet. So they produce similar amount of flux. And so with a postdoc in my group, Daniel Sebastian, we were looking at this. And here I'm showing a paper that just got accepted again, where we recover now the faint secondary star using traditional spectroscopy. But importantly, we recover it at every part of the orbital phase. So this is a phase curve obtained from the ground, whereas most phase curves, and I forgot to mention then, the phase curves that I was showing you, if you ask among exoplanet astronomers, they all would tell you that you can only do that using a space telescope. But actually what we show here is that you can recover it at a high with high resolution spectroscopy from ground-based telescopes, and we recover it all along the path. So this is normal, okay? The star is as bright during day than it is during night, and that's because it's a star, so it's bright on every side of it. If it were a planet, we would see that the signal would have disappeared here and here, leaving it strong in the center. And so now we are thinking of applying the same methods, and so we're applying now for telescope time, actually at the European Southern Observatory, to do the phase curve of an exoplanet using this kind of method. We can also recover it here as a function of wavelength. So this signal that you see here is a signal of that star, which is faint in blue wavelengths and brighter in redder wavelengths. So we can recreate, not just find out that the object exists, find out what molecules are there, but we can also recreate the overall shape of the spectrum. And now the idea, the next step is actually to do it on an exoplanet and map out where carbon monoxide is on the planet versus where, for instance, methane would be, etc., etc. So the idea is to eventually use this method to map out molecules on exoplanets. So that's one bit. Now I'm going to move to Antarctica, and you're going to see that some themes start coming all together. And I should almost finish in a few minutes, right? So, yeah. So what are we doing in Antarctica? So what we do is specializing in very long planetary transits, and in particularly rare transits. And the reason we do that is because we have a very long night. And so it means that if there is a rare event, we're almost certain to be able to observe it. Whereas, as we know, from every other observing site in the world, it either happens during the day or when it's cloudy. But in Antarctica, it's night all the time, and it's bright sky all the time. The other thing that we can do is do asteroid follow-up, and we also are searching for interstellar visitors like Oumuamua. And the reason we can do that is because we are located near the anti-apex point of the solar system, so we look at it, but also because we are outside of the ecliptic plane of the solar system, so many of the near-Earth asteroids or main belt asteroids, we actually don't even see them, so they're not a source of contamination for us. So that's the idea. It's a very strategic location. I will pass you on, but it's a fantastic place to go. That's our telescope here. This is where we live. This is us working on the telescope. Because it's a philosophy department, I thought I would bring a little bit of philosophy as well, but it really felt, to me, it was really weird for the first time to actually go beyond habitability. And people tell you that there is nothing in Antarctica. On the plateau, there is nothing. It's weird to contemplate nothingness, because even though people had told it to me, like, to see it and experience it is weird. And it actually regained my interest in detecting life, because all our senses effectively are affected by life around us. There is not a single smell out there because there's no organic matter. There is no movement. It's impossibly flat, like the ocean, but at least the ocean is moving. There is not a single sound. It's really empty. And on the senses, it's actually quite fascinating to experiment. But anyway, so now I know what it's like to not be habitable. I'll pass quickly over the advantages of Dome C, but we have a nearly continuous night from mid-May to the end of July. We actually started acquiring data for this season just a few days ago. We're testing the new telescope mount at the moment. We have great weather, we have very low atmospheric pressure, and then also we have 10 times less water vapor in the atmospheric column than from the best other sites in the world. And because the seeing conditions, so how sharp our images can be twice better than in the Atacama Desert, it means that we would have 4 times less background just from that thing alone. And in addition, the atmosphere is cold, so we have cold optics and cold sky. And so overall, I think that a 2-meter telescope would do a similar signal-to-noise ratio on an exoplanet than the 8 meters telescope that we have in Chile. And so it means that at the moment, when you apply for an 8-meter class telescope, you apply for maybe 10 nights at a time, 3 nights at a time. You can't do much with that on an exoplanet. And most of the high-resolution spectroscopy work that I was telling you about is usually done by 5-hour chunk. So people apply for 5 hours and they make the paper out of that. If we build a 2-meter in Antarctica, we can stay 2 weeks on it, on the same star, on the same planet. And that's how we're going to get maps of molecules. And so that's my goal. Build a 2-meter in Antarctica. To show you that it's possible, here is a very little known paper, possibly the first detection of a phase curve in 2013, 10 years ago, from the ground. Most people have forgotten that. This was 3 weeks of continuous data from Antarctica. In addition, you remember circumbinary planets? Not a single transit of a circumbinary planet has ever been done using a ground-based telescope, and it's because of that motion of the binary plus various 3-body effects. Well, we've done it 4 times from Antarctica. And finally, Here is a long period transiting planet. So this is 140-day long. You can see this line curve here is 36 hours long. The transit itself here is 12 hours. So a night in Chile would be a chunk of the transit. You wouldn't see anything. And you can see here is the sky. So the interruption here is because there was just a small twilight during the transit. So this is a world record. This is the longest period planet ever observed from the ground in transit, and we've done it twice, showing how interesting Antarctica is. It really opens up a new way to observe the sky. And so around this kind of planets, our idea is to create a catalog of temperate gas giants and then hunt for the presence of moons with James Webb. So I'm finishing here. I hope I've convinced you of two things. First, it's really important to observe alternate environment to single sun-like stars. Ultra-cool dwarfs have a unique role to play in searching for rocky planets, notably thanks to Speculas, and binary stars have another role to play to study planet formation, but also identify new temperate worlds, but also that alternate environments on Earth, like Antarctica, would be particularly good for research. And here are all the people I work with. Thank you.